talking about linear equations and how to solve them. If you remember all the way back in the first module that we did, we talked about solving some equations and how to do that, and in general they were linear, and so we explored some methods to do that. We're going to formalize some of those methods now, and we're also going to begin to look at how the solutions are structured and how we can tell how many solutions there are. This will probably be broken up into a few different videos since there's a lot to talk about. So first, let's talk about some properties of equalities. We're going to start with the addition property of equality, which says, we've actually used this before without explicitly stating it, that if you have a number x and that's equal to y, then if you have another number a, x plus a is equal to y plus a. So this is probably a good thing to put as an example. Let's say that x is 5. That tells us that x plus 2 is 5 plus 2, which is 7. That's the addition property. Very much related to the addition property, as we discovered last time, is the subtraction property. Remember, subtraction is just the inverse of addition, so it's actually covered under the same the same property, but we'll go ahead and spell this out here. If x is equal to y, then x minus a is equal to y minus a. So again, if x is 5, then x minus 2 is equal to 5 minus 2, which tells us x minus 2 is 3. Then we have the, one day I'll spell multiplication right, multiplication property of equality. And what that says is that if x is equal to y, then ax is equal to ay. And likewise for division. So remember, division is just pretty much the inverse of multiplication. If x is equal to y, then x divided by a is equal to y divided by a, provided that a is not 0. So these are the two properties, but really four properties, but really it's just two properties of the real numbers. As far as the properties of equalities, we have the addition property of equality, which also covers subtraction, and we have the multiplication property of equality, which also covers division. Now, using these, I guess maybe I should use some examples for multiplication. So let's say we have x is 5, then 2x is going to be 2 times 5, which is 10. Division, x is 5, then x divided by 2 is going to be equal to 5 divided by 2, which is just 5 halves. So these will become way more apparent why we need them in just a few minutes. Now let's talk about solutions to equations. And this is going to be, in particular, linear equations. The word linear should remind you of a line. And so a line in two-dimensional space, let's say you have two lines, and I'm going to need a few different charts here. We have this line, which is represented by equation 1, and we have this line, which is represented by equation 2. Notice they're parallel, so they're never going to cross. The intersection point is where we would say that it obeys both, and let's actually look at one with an intersection point. Let's say we have, and really I just need to redraw that whole thing. Let's say we have this line and this line. Then this point is on both lines. And maybe let me make that red so that you can see it. That point is on both lines. It's on this line and it's on this line. So it obeys both equations. So this is what we would call a solution. We would say there's one solution to these two equations. Up here, if the lines are parallel, they never cross, so there's no points that's on both lines. So there are 0 solutions. And then on, there is one other case where if both lines are plotted on top of each other, whoops, I wasn't supposed to delete that, sorry. If both lines are plotted on top of each other, then there are infinitely many solutions. So let's look at how we can characterize those. Let's first look at 3x, or 3 times x plus 2, 18. The first thing we need to do here is multiply. So we will use the distributive property and say, well, this is 3x plus 3 times 2, it's 18. So we get 3x plus 6 is 18. Now we can use the addition property of equalities, or we could use the subtraction property of equalities. And I'm going to go ahead and use the addition. And we can add -6 to both sides. And now we can use our inverses. Well, we'll use the associative property first to group these two together. And then on the right side, we'll say 18 plus -6 is going to be 12. And now we can use the property of inverses, of additive inverses, to say that this is going to be the additive identity, which is 0. 3x plus 0 is 12. Otherwise, just known as 3x is 12. Now we can use the multiplicative property of equalities and multiply both sides by 1/3. And we can use the associative property on the left side to group those two together. And then 1/3 times 12 is 12 divided by 3, which is 4. And what this corresponds to is the case where we have parallel lines. And you can see they don't cross anywhere. So whenever we're trying to solve for a crossing, it's going to end up being false because they never cross. And then let's look at the case where there are infinitely many solutions. So let's say we have 3x plus 6 is going to be 1/2 of 1/2 of 6x plus 14 minus 1. Well, kind of simplifying like we did last time. We can distribute, we get 1/2 of 6x plus 1/2 of 14 minus 1. 1/2 of 6x is going to be 3x. 1/2 of 14 is going to be 7. And we can continue to simplify. And we can add negative 3x to both sides. On the left. Note resolves to identity, so we get 6 to 6. So no matter what x is, this is going to be true. So if you get something that is always true no matter what x is, then there are going to be infinitely many solutions. And this corresponds to the case where we have two lines that are plotted over each other, and they intersect infinitely many times. And those are the three options they can be. They can either be one solution, which is where they cross once, no solutions, which is where they never cross, or infinitely many solutions, which is where they cross everywhere. There are no other options for linear equations. Next time I think we'll just work through some examples on this, since we went through it kind of quickly, and it'll probably be a